So how do we start solving a linear system? Well, what we're going to do in this section is build a suite of tools that we can use, hopefully strategically, in order to take a system of equations whose solutions we don't yet know and replace it by another system of equations that is hopefully simpler than the one that we started with and which has all the same solutions as the original. So that's the strategy. We want to take a messy system and kind of just tweak it a little bit in ways that make it less messy, but which do not change the solutions that it has. And if I can do enough of those tweaks to where I can get it down to the simplest possible form, then it's in that form that we're going to be able to make the choice of, okay, which variables should we assign to free parameters, and then which ones are going to be bound by those free parameters, and then be able to describe the solution set from there. And so the suite of tools that we develop is called the elementary row operations. So this section is about getting used to those elementary row operations and how they work. This is also the place for me to put up a caveat for our course. And that caveat is that this section and this learning standard E2 on row reduction of matrices is going to be the only standard during which I'm going to expect to see your pencil and paper row reduction work, right? So when you apply these strategies, this will be the one time that you'll be applying them with your own pencil paper mental arithmetic. After this, so after we clear this section and get on to bigger fish to fry, it is totally okay with me if you prefer to use technology to do this row reduction process. In fact, I recommend it because what I don't want is I don't want you to be spending so much time doing all the mental arithmetic and row operations that you miss the bigger picture of linear algebra, which is a very real thing that could happen, as many students who have taken linear algebra in the past and had to do all their calculations by hand can attest to. So all that, which is to say, technology is a go as soon as we get out of this section for any and all row reduction that you would need to do. And almost every process that we do for the rest of the semester is going to involve this process of elementary row operations at some level or another. So let's dig into it. And the first definition is, I sort of alluded to it before. What kinds of systems are we, how are we allowed to change a system of linear equations? How do we know that we're not totally screwing things up if we go in and we start to monkey with the equations or the variables or the coefficients or whatever? And this is our standard for not mucking things up. The standard is, as long as the new system has all the same solutions as the old system, we're okay, right? And so two systems of linear equations that have all the same solution set are called equivalent systems. And we can spot equivalence at the level of their equations. We can spot equivalence at the level of their augmented matrices. And at the level of augmented matrices, our authors of our textbook use the little squiggle in the middle to denote that these two augmented matrices are equivalent. They correspond to equivalent systems of linear equations that have the same solution set. So where we begin in this process is in investigating this first activity, 1, 2, 2, where you have 7 different possible things that we could do with an augmented matrix. And your first job with your team is to figure out which ones of these 7 actually can change the solution set of a system and which ones do not change the solution set of a linear system. So there's a bunch of choices. Take 2 rows of my augmented matrix and swap them. Take 2 columns of the matrix and swap them, et cetera, et cetera. So take a look at each one of them and decide, does it change, could it change the solution set, or does it definitely not change the solution set of a system of linear equations? And so for the ones that don't change the solutions, mark them as valid. For ones that might change the solutions, mark them as invalid. And keep in mind, and this is a good place to practice, the connection between augmented matrix and the original equations, right? That the columns of the augmented matrix on the left side of the vertical bar correspond to the variables, the unknowns. The rows correspond to the equations. So whatever we're doing to columns and rows of the augmented matrix, you can think of as we're doing things respectively to the variables or to the equations in our original system. And remembering that, I think, will help you to suss out which ones of these are valid and which ones of them are not for creating an equivalent system. Of these 7 things that you might consider doing with an augmented matrix to try and make it simpler, to try and discover what its solution set is, some of these are valid things to do because they produce an equivalent augmented matrix which has the same solution set as it had before. Some of them are not. Some of these are things that you should never think about doing again, as far as our semester is concerned, unless you are interested in destroying the solution set potentially to the thing that you're trying to solve. Let's just check in real quickly. Maybe I'll have you write in the Zoom chat. What was your list of all of the invalid things, all of the things that we can't do? Take a moment and type yours into the Zoom chat. Before we get there, there is a question that I want to get to first. So we have agreement among all 3 of your teams about which ones of these we can do and which ones of them we definitely should not do. The things that we can do include swapping 2 rows. So somebody give me a justification. Why is this okay? Why does this not change the solution set of a linear system if we take 2 rows of the augmented matrix and you just swap their places? So we can always get away with swapping 2 rows because, as you say, all that does is it trades places of 2 of the equations in our original system. And since a solution has to satisfy all the equations at the same time anyway, it doesn't matter if we change the order of the equations, right? So we can swap rows. That's not a problem. What about D? This was one of the other ones that you agreed was a valid operation. How come we can get away with multiplying a row by a non-zero constant? Why does that give us an equivalent system? So when we multiply a row by a non-zero constant, what we're doing is multiplying both sides of one of the equations by the same non-zero constant. And that is one of the first things that we ever learn in algebra that is okay to do to an equation that's not going to change its solutions. One of the reasons for that is that if I multiply by a non-zero constant, I can always redivide that non-zero constant back out and get back to where I started from, right? So the new equation has all the same solutions as the old equation did if I just multiply by a non-zero constant. And so the most sort of complicated one that you still concluded was valid was this part E, adding a constant multiple of one row to another row. So tell me, how are you processing that example? Like, why is that a valid thing to do to a augmented matrix? We already convinced ourselves that multiplying a row by a constant was okay, right? Non-zero constant was okay. And so it's really the addition part of this that gets us to think a little bit in new ways and different ways. And I agree with what you just said. The reason that adding 2 rows of an augmented matrix doesn't change the solutions is that a solution that satisfies both of those equations in the first place, well, each one of those equations is the same value on the left side of the equal sign as it is on the right side of the equal sign. And so if we add the left-hand side of one equation to the left-hand side of the new equation and the right-hand side to the right-hand side, we are adding the same quantity to both sides of that second equation, which again is one of the first things that we learn about in algebra as something we can do to an equation. Add something to both sides of an equation and we have not changed the solutions that that equation has. So A, D, and E were the valid ones. Let's take real quickly and look at one example of an invalid operation just to kind of try to convince ourselves of why that operation was invalid. So what about swapping 2 columns? What is our thought about why should we be suspicious of that? Why can't we do to columns here what we were okay to do with rows? Swapping rows was okay. Why is swapping columns a problem? If we try to swap columns, we are changing the assignment of which variable goes to which column, right? So if I change the first and second columns, if I swap them, right? If my original system maybe had a solution of 4, 12, then after I swap the columns, that new system is going to have a solution that looks like 12, 4. Right? So if I change the meanings of those variables, then I definitely am probably changing my solution set. Unless we get so lucky as to have a solution set that consists only of like multiples of 1, 1, 1, 1, 1 or something like that. Like all the numbers have to be the same. All the coordinates have to be the same. Then it wouldn't notice. But it's not something that we should ever do if we don't already know what the solution set is, because swapping the variables does change the nature of our solution set. So as it turns out, these 3 options, A, D, and E, And this, in some linear algebra courses, is worth proving. We won't do that today, but you can actually prove in linear algebra that those three things are in fact the only three things that we can do that are guaranteed to produce an equivalent linear system at the end of the process. Now, we can do as many of those as we want to in succession, as many of those as we need to get our system to be as simple as we need it to be. But those are the only three tools in our toolbox for making a system of linear equations simpler. And so our job now is going to be to figure out how to use those strategically, rather than just sort of, blithely decide, well, maybe I'll swap a row now. Well, maybe I'll multiply this row by this. How can we sort of develop a way to be mindful about how we choose these steps so that we can try to get to the simplest form as quickly as possible? So here are the notations that we often use for these. If we're going to swap two rows, usually we'll write somewhere in the margin row 1 and a little double arrow row 2, just to sort of convey to the reader that that's what step is happening there. We can also multiply a row by a non-zero constant. So 2 times the first row becomes the new first row. This is kind of funny programming assignment language. If you're a computer science major, your eye might be twitching a little bit how we're using this here. But it just means take twice the first row and make it the new first row. And then the third one is to add a constant multiple of one row to another. And again, using this assignment sort of notation, take -4 times the first row and add it into the second row, and then make that the new second row of my matrix. So those are the three tools in our toolbox for getting a new augmented matrix that's equivalent to the one that we started with.